Assalamu alaikum dear students, welcome to the online lecture on MATLAB simulation of nonlinear and linear control systems. Today we are going to discuss this paper from IEEE Transactions on Automatic Control, published in 2012. The interesting thing about this paper is that it proposes a chattering free digital sliding mode control as opposed to the continuous time sliding mode control that we have been discussing mostly in the previous videos. This one is the digital and with state observer and disturbance rejection. So the authors say that the digital sliding mode control fully exploits the multi-valuedness of the dynamics on the sliding surface, and due to time discretization there are some chattering is avoided. So without further delay, let's see how what kind of things they have proposed and how can we simulate them in MATLAB. So H would be our time step. So in discrete time systems there are time steps as opposed to derivatives in the continuous time systems. So the difference between tk plus 1 minus tk, that would be H, a positive time step. M will be the discrete time sliding surface, and its surface will be co-dimension M space of the state space if the state space satisfies certain properties. I'm not going to go into the detail of these properties because it requires a very long discussion of dimensions and spaces and so on. You can download this paper, read it through, and get into the theory. But I think there is a small typo here, because they define a sine function or this sort of a modified sine function where it has a value plus 1 if x is greater than 0, and I believe it's minus 1 if x is less than 0, and the value ranges anywhere between minus 1 and plus 1 if x is equal to 0. So this is really different from the conventional sine function where x is equal to 0 means that the function will have 0 value. In the simulations I will be using the conventional sine function, but we will see what difference it makes, or maybe it does not make any difference, at least for the parts where we simulate the systems proposed in the paper. So first system proposed in the paper is the first order system, x dot equal minus a tau plus phi, where tau belongs to sine of x. So instead of tau equal to sine of x, tau belongs to sine of x because of this different definition of the sine function. So we will be using the conventional sine function in our simulations, but you can choose the function proposed by the authors, and even the conventional sine function lies within the definition of this sine function. So even if you are using conventional sine function, it satisfies this definition of the sine function. So this is the discretization of the system. So looking at this discretization, x of k plus 1, they defined an intermittent variable x tilde of k plus 1. So x tilde of k plus 1 is equal to x of k minus a times h times tau of k plus 1, where tau k plus 1 belongs to sine of x tilde of k plus 1. Now here you can see a problem that x tilde depends upon tau k plus 1 and tau k plus 1 belongs to the sine of x tilde. So this will create a little bit of a problem, but they have pointed out how to deal with this problem a little bit, and I have found my own way of dealing with this problem. So xk plus 1 is equal to xk minus a times h times tau k plus 1 plus h times phi k plus 1, which is the disturbance. So I have done some simulation of this file just to check So for example, if we go to discrete SMC part 1, so let us suppose we are going to run this file for 10,000 time steps, and we choose this. A is the upper limit of the disturbance function, so this disturbance function should be upper bounded by value A, which is here. So A I have chosen to be 1.5, that means my disturbance will be so I have chosen my disturbance to be random. This is a random vector using the rand function in MATLAB. So it generates a random number between 0 and 1. So disturbance can be any random number between 0 and 1. In this case study I have generated myself, this is not given in the paper, so it's just to test what they claim in the paper. So so x is will be of course of the number of time steps, and this is the step size 0.001. It's a 1 over 1000. So it's about 1 millisecond of time step. So I start with initial condition 4, and I use the for loop to calculate this discrete time difference equation. So xi plus 1 is equal to xi minus a times h times tau of k. Now I have defined tau of k to be sine of x tilde, where x tilde is x of k minus a times h times now this sine of xi, this is tau of k. So here, instead of using tau of k plus 1, in the code I have used tau of k, which is just the sine of x of k. So here the time step is represented by k. Here in the for loop, time step is represented by I. So x of I plus 1 is x of I minus a times h times sine of this whole thing, which is basically tau of k plus 1, which depends upon tau of k. And this is the disturbance h times the p of I plus 1, which is this thing right here. So and then you can define the time to be 0 to k minus 1 times h with the time step of h, and then you can plot t versus x. So let's see what happens. So when we run this file, so we get from the initial condition 4, the state variable converges to 0, and if we zoom this in, so you can see here that due to the disturbance there is some chattering in the state, but that is about they claim, the authors claim that the disturbance or this type of chattering will be about 1000 times less than the it will be attenuated by the factor of h. So disturbance will be attenuated by the factor of h. That is what is depicted by the paper, and that is roughly what we see in the simulations as well. So let's keep going and see what else this paper has proposed. So this was the first order system. Let's go to some more. So for example, this system of equation 13, let's try to simulate this one. So for this system, let's go into the second file. So we have we have x of k plus 1 equals xk minus a times h of tau 1 of k plus 1 minus alpha times h times tau 2 of k plus 1 plus h. So all of this is written here inside the for loop, but before the for loop I have chosen the number of steps to be 10,000. Again, the upper bound on the disturbance is 1.5, and alpha I have chosen to be equal to a. And if you look into the let's see. So disturbance once again has to be chosen to be a random number between 0 and 1, and the initial conditions x, the initial condition of x is 4 and the initial condition of e is -3. And if you look at the equation, so this is xi plus 1 is equal to xi minus a times h times sine of xi minus a. This is the same strategy that I used in the previous example when I simulated equation 4. So instead of tau k plus 1, let me see if there is there it is, equation 11. If you look into the equation 11, then you can see that x tilde, again these two are intermediate variables which are used for xk plus 1 and ek plus 1. So coming back to the code, so this tau k plus 1 belongs to the sine of x tilde k plus 1, where x tilde k plus 1 is x of k. So it is sine of x of k minus all of this thing. Instead of here again tau k plus 1, I use tau of k here, and this tau 1 is tau k, x tilde k plus 1. So this is a little bit of a difference that I have created from the proposed model. And then minus alpha h sine of e minus, so again the same strategy has been used here. You can, by the way, just I've maximized this file so that you can pause here, pause the video, take a screenshot, and copy this code, run it, study it, and then you can understand in a more deep manner what I have done, because all I have done is that instead of here using tau 1 of k plus 1 as the sine of x tilde k plus 1, because it is inside the equation of x tilde already, so I have used it as sine of x k plus x of k, sine of x of k. So this is sine of x of k, and this whole thing is equivalent to x tilde. Rather I have a small mistake, or I think I should have minus alpha. Okay, no, that one is here, minus alpha times h times sine of e minus, yeah, this one is separate. So this is tau 2 of k plus 1, and once I run this, so then this should be, so this gives you can see that the initial condition of x was 4 and the initial condition of e was -3. So both of these state go to 0. By the way, these results are highly dependent upon the size of the step h. So if you select h to be, let's say, 1/100 or 1/10, then the results will be slightly worse. Let me try to make this a little bit smaller, and let's see what happens. So you can see here that the magnitude of the fluctuations, that will of course increase. Here the magnitude of fluctuation is from 0.4 to -0.4 at almost. But if I decrease this step size, then the size of fluctuation also reduces, which is what has been claimed in the paper, because they say that, you see that it's 10 to the power -3, so almost 10 times reduced. So the size of fluctuation is directly proportional to the step size, which is exactly what the paper has claimed. And next I want to show you the simulation of if you keep going in this paper, there are many mathematical equations and derivations, but here in this numerical simulation part, they have simulated this h step size of 1 over 10 and using zero order Hall filter with the disturbance equal to phi sine omega t, and a is equal to 1, alpha equal to 2, and all these values they have simulated the system in the equation 10. So if you go to equation 10, the system in equation 10 is this one. So this one is the system in equation 10, that almost the same one that we simulated in discrete time. If we go, this is the equation for this system. So you can see here that alpha is equal to 2, omega is equal to 5, a is equal to 1, phi is equal to 0.1 sine omega t. All these values are given in the paper, and tau I have selected to be conventional. So these are the sine functions defined in the paper, which are special projection type sine functions, but I have defined them to be conventional sine functions, which by the way satisfy this definition, so it is within the theory. So x dot equal minus a times, so these are simple dynamics. So I can run these dynamics using my script file which calls these dynamics, and I run it for only 7.75 seconds, because I mean for 0.75 seconds it takes at least quite a few seconds to run. But after the run is complete, you can see here both the states have converged from their initial state to 0, and there is very little amount of chattering, or that's because the magnitude of disturbance was already of the order of 0.1 or something. So you can see here that this is 0.1 sine omega t, and it is attenuated 10 well, it has been attenuated more than 10 times. The results are quite good, but this is for a change, this is these are the not the discrete ones, these are the continuous time. So this is continuous time dynamics, equation 10 here, and it has been run using this file. So I run it again, and I can show you the fluctuations are quite small. Yeah, so you can see the fluctuations. If I look into that, these are of the order of 10 raised power minus 5 or something. So this is like 10 raised power minus 5 and something like that, 3. Okay, so next I want to simulate a system that has been proposed here, that includes an observer as well. So let's see how that goes. So we have just simulated this one. So we keep going, and they have proposed so yeah, here there's a finite time velocity observer design. So observer is almost the same as any observer is, x hat equal y hat plus no, actually it's not the same. It's a little bit of a different approach. Of usually an observer is copy of the system dynamics along with some correction term. There is a correction term involved here, x minus x hat, sine of x minus x hat, as sort of like a function that depends upon the correction term. Here there is a correction term, and then but the idea is a little bit different. So the full system with observer is given here in equation 60, where x tilde y tilde are intermediate variables, and x hat and y hat are observer dynamics, and x and y are the state variables, if you will. and then tau 1 and tau 2 are the control that depends upon the, so tau 1 depends upon the x tilde and tau 2 depends upon y hat. And let's see how we simulate this. We go to this file. So here again, the steps, number of steps I have taken 2000. Here mu is equal to 1, it's given. So this is this mu, and it is given in the paper later on, its value. V is equal to 2, it's also given in the paper. H is equal to 0.01, k1, k2, k3, k4, all these values are given in the paper. And this is the like initialization of the variables x, y, x hat, y hat, and x tilde, y tilde I do not define in the code. I just use them, use their equations instead of using the variable names. So p is equal to 0.1 sine omega t, where omega is 5. So this is also given in the paper. Initial conditions are the same that are given in the paper, as opposed to the previous. So this example I created by myself. It was not given in the paper. This example I created by myself. This is something, this continuous time was given in the paper, and this is again, this is from the paper as well. So 2 examples from the paper and 2 examples that I have created by myself. But in all of these examples I have done a little bit of difference. From, instead of taking the projections and so on, I have just defined wherever I can, I see, sort of a non-causal or a questionable definition of tau, then I use the previous time step instead of, for example, if there is tau k plus 1 in the y hat k plus 1 and y hat k plus 1 is used, let's say in it's not used in y tilde, but then this y tilde is used, where is it used? Let's see, y tilde, we don't have y tilde here. We have y tilde. I am unable to find y tilde anywhere. But anyways, so giving you an example, here it is. So y tilde is used in x tilde, and then x tilde is used in the tau 1 k plus 1, but tau 1 k plus 1 uses x tilde, which appears in y tilde. So if we load, so this is required to calculate this, and this is required to calculate this, but this is using something, so this is required to calculate y tilde. So y tilde is required to calculate x tilde, x tilde is required to calculate tau 1, and tau 1 is required to calculate y tilde. It looks like, some sort of an infinite loop or something. So you cannot have, this sort of thing. So you somewhere you have to go to the previous time step. So here what I have done is that y hat k plus 1 is y hat k minus h times mu tau 2. So so tau 2 is defined to be y hat, the sign of y hat, which is basically what we are, tau 2 is appearing within y hat is using tau 2, and tau hat is using y hat. It cannot happen, so what I do is I use y hat I instead of y hat I plus 1, because y hat I plus 1 is what I am computing using this. So here I have used y hat I. So, and similarly h times v times sine of xi plus h times k3 times sine of xi minus xi x hat. So you can see here at certain places I have used xi instead of x tilde k plus 1. here x tilde k plus 1 is xi plus h times y tilde k plus 1. So where y tilde k plus 1 is this whole thing. So substituting these, I have computed this code. I will maximize this so that you can take a screenshot of the video at this instant, and study the code a little bit. It matches with the paper, but not exact match, because at some places I had to make my own decisions. Paper has provided ways around it, but those are based on the projections, and I am really not comfortable with the projections. Although you can go ahead and do the projections as proposed by the paper, but this method, this works, I mean, pretty well for me. Xk plus 1, that is xk plus h times yk. That's an easy one. So yk plus 1 actually, so that's an easy one. So once you're done, you can plot t versus x hat, t versus y hat, t versus x, and t versus y, and we can run this, and you can see the results here, that all the states and their estimates. So x hat is very similar to x, and it goes to 0, and similarly this y hat, this is y hat, so y hat is very similar to y, although the initial conditions are quite different. So we can also plot x hat and x together, and y hat and y together. So then we will have to call this y, and we will have to call this y hat, and we'll have to call this x hat, and we'll call this x. So let's see how they compare. We run this file, and you can see here that this the state estimation is quite well. So this is x hat and x, quite good tracking, and similarly this is y hat and y, although initial conditions were different, but the estimate of y, which is y hat, it caught up to the actual value of y, and the things are good and we are happy. So that's all for today, and I hope that it will keep you going in the discrete time chattering free digital sliding mode control. Thank you very much for listening, and stay tuned for more videos on MATLAB simulation of control systems. Have a good day.